In this lecture, we are going to discuss the application of time-dependent perturbation theory to the subject of light-matter interactions. In particular, we will discuss the semi-classical theory of light-matter interaction. What this means here is that we are going to treat the atoms involved as quantum mechanical, as we must, but the radiation or the electromagnetic radiation interacting with the atoms will be treated as an external classical field. So, radiation will not be quantized. Now, it may come as a bit of a surprise that most phenomena in light matter interaction can actually be explained quite well within this approximation. Almost 99% of the phenomena that we see all around us does not require you to think of electromagnetic radiation as a quantized object. And what that means is that we do not need the photon at all to explain 99% of the ways in which light interacts with matter. And this may come as quite a surprise given the fact that the photon was instrumental in the history of the development of quantum mechanics. But again, quite surprisingly, you can even explain photoelectric effect quite well without treating light as a quantized object. So you can have photoelectric effect explained perfectly well without photons, but you do need quantum mechanics. You have to assume that matter is quantum mechanical. So within this approximation, we need to understand how to describe electromagnetic radiation in terms of a classical field properly. And just to point out that classical mechanics already gives us a way of understanding how to treat external radiation. If in the absence of external radiation, the Hamiltonian describing a system is H0, which is given by kinetic energy terms, plus say the Coulomb interaction between the charged particles in the system, then if you turn on electromagnetic radiation from outside, the Hamiltonian changes basically by insisting that the momentum is no longer mx dot, and the momentum changes. As a result, the kinetic energy term now ends up looking like this. So instead of pk, where you had pk before, now we have pk minus ek by c, a, where a is a vector potential, which of course is a function of the position here and position of the kth charge. Now, this is called minimal coupling. In addition to this, you may have an additional term which comes in because the charged particles may have permanent magnetic moments and the magnetic field of the radiation may interact with those. Now, in what is to follow, we are going to simplify things somewhat by assuming that the nuclei involved in the process in these atoms that we are talking about are infinitely massive. As a result, we can stop worrying about the dynamics. So the only dynamical entities here will be the electrons. And we will also ignore the mu dot b term, the magnetic moment effect, because typically that's pretty small. So with these two approximations, all the m's that are there in your problem will be the mass of the electron and all the e's will be the charge of the electron. And now let us take a look at a bit of electrodynamics. So what I'm going to say next is something you have all studied in classical electrodynamics, but a bit of recap is necessary just because we are going to use these results soon. So what we are going to do is describe the system in the Coulomb gauge, and in the Coulomb gauge the zeroth component of the vector potential is taken to be 0. So this is the 4 vector potential we are talking about, and the 3 vector potential has a divergence which is set equal to 0. That is the Coulomb gauge. Remember, the curl of A is a magnetic field and you are allowed to change the vector by adding some scalar function, some vector function to it, as long as its curl doesn't change. This is the so-called gauge freedom that we have, and by exploiting the gauge freedom we can put in various gauge conditions, and the one which is convenient for us right now is a Coulomb gauge where the divergence of A is 0. Why is this convenient? We will see soon. So let us consider monochromatic radiation where the vector potential obeys the Coulomb gauge condition, and let's think of a monochromatic plane wave. So the vector potential in this case, A, which is a function of both r and t, of course, is a0 vector e to the ik dot r minus omega t plus a term which is the complex conjugate of this. Notice that this is not an operator. There is no quantum mechanics involved here as far as the radiation is concerned. So this is a vector valued classical object, and this is just a plain complex conjugate, so that the overall vector potential is real. And here, of course, the wave vector k, which denotes the direction in which the wave is propagating, has to obey magnitude of k is given by omega by c, where c is the speed of light. That is essential so that the electric and magnetic fields which come out of this vector potential actually satisfy Maxwell's equations. And in addition, the vector a0 can be written down as a vector magnitude, which is a real number, times a quote-unquote unit vector epsilon. The reason why I put the unit here within quotes is that this epsilon vector can in general be complex, and when you say unit vector, you mean unit norm using the norm, the inner product of complex vectors, that is a star dot b. So just for as an example, if you take k hat, the direction of propagation, k hat is the unit vector in the direction of k, to be z hat. Notice that I am deliberately using x hat, y hat, z hat rather than I, j, k for unit vectors along the x, y and z axis, simply because I want to reserve k hat for the vector which denotes the direction of propagation of the wave. So if k hat is z hat, then the polarization vector would be perpendicular to that. That has to be the case because otherwise that follows from divergence of A equals 0. And two possibilities immediately present themselves. Epsilon can be epsilon x, which is x hat, or epsilon y, which is y hat. These obviously describe linear polarization. The electric and magnetic fields which come from this, from an A with this value of epsilon, will be polarized along the x and the y directions respectively. Of course, not only these, any real combinations of these two vectors will give you linear polarization. Complex combinations can give rise to other polarizations. For example, epsilon plus, which is essentially x plus iy apart from a factor in front, and epsilon minus, which is x minus iy apart again from a factor in front. These describe left and right circularly polarized light respectively. The presence of the imaginary term here, this in x plus iy here and x minus iy here, essentially ensures that there is a phase difference of 90 degrees between the x component of the vectors and the y component of the vectors, and this leads to circular polarization. We will see a more detailed explanation of this in the next slide. So how do you calculate the electric field and the magnetic field from this? The electric field follows immediately from minus 1 by c del A del t, and if you do the derivative, it automatically works out to be this. This is pretty straightforward. When you differentiate them e to the minus I omega t here, which is the only term which explicitly has t, you get minus I omega, and that coupled with the minus 1 by c here gives you plus I omega by c, plus of course the complex conjugate of this term. The electric field of course is real, so it's this vector plus its complex conjugate. Similarly, the magnetic field is curl of A, and curl is easy to see, you get ik in front, and this is what the magnetic field is. Again, this is one term plus its complex conjugate. Well, again going back to our example, let's take k hat to be z hat, so not k vector. K vector of course has magnitude omega by c. So this is a typo here. This should be the unit vector in the direction of k. If it's z hat, so the wave is propagating in the z direction, as you can see, that means the electric field and the magnetic field both will be propagating in the z direction, because this term here will be to the ikz minus omega t. Let's take for an example the special case where the polarization vector is epsilon plus. If you just use the expression for epsilon plus that was there in the last slide and calculate ER using this, taking care to involve the complex conjugate, you will find that at r equal to 0, say, E vector is going to turn out to be root 2 times mod A0 into omega by c. These are factors which come from the omega by c here and so on, times, and this is the important part, cos omega t x hat plus sin omega t y hat. This means that at t equal to 0, the electric field points in the x direction, and as time increases from 0, the electric field component along x slowly decreases, whereas the component along y starts rising. This means that the vector is going to rotate, as you look down upon it from the z-axis, is going to rotate from the x-axis towards the y-axis. That means rotate counterclockwise. And if you imagine that you are walking along the tip of the electric field vector, at every point you are actually turning to your left. This is what left circularly polarized light means. Of course, I have taken r equal to 0 just to make this expression look a bit simpler. You can easily figure out that the same thing happens no matter which r you take. So at every point, this electric field is rotating counterclockwise, as you are seeing this by looking from the direction towards which light is going, and this is what LCP here means. Okay. The other important quantity that we need to worry about from classical electromagnetism is the rate at which energy is carried by these fields. So we have the electric and the magnetic field, whose cross product gives us the Poynting vector apart from a factor of c by 4 pi. I must mention here that we are using the Gaussian system of units here. So if you are using SI, some of these factors will be slightly different. I am pretty sure you can put in the correct factors in those cases. And now, of course, what you will get are rapidly oscillating terms, and you need to be able to take averages properly over time in order to get an idea about how much energy is flowing per unit area per unit time. So the Poynting vector comes out to be c by 4 pi times E cross H as average, and it may take a bit of care to calculate this out, because when you take the cross product of E with H, there are going to be 4 terms, right? There are 2 terms in E, 2 terms in H, so the cross product will give you 4 terms. Out of which, for example, that if you took the cross product of these 2 terms, you will end up with e to the I twice I k dot r minus omega t, which is a rapidly oscillating term and whose average will be 0. So the non-zero terms will actually come from the cross terms here and here. So once you do this correctly and take the averages properly, you will find out that this works out to be 1 by 2 pi omega square by c A0 mod square times k hat. So the propagation of energy happens in the same direction in which the wave is going, in the direction of k, and the factor in front, which is the magnitude of s, tells you how much energy is flowing per unit area per unit time. This, of course, is what we call the intensity of light, and so at least for monochromatic radiation, intensity of light is directly proportional to the square of the amplitude, and you multiply this by omega square by 2 pi c. And very often we talk about the number of photons crossing per unit area per unit time, and that can be easily figured out here by just equating this intensity to n gamma times h cross omega being the energy carried by each photon. Of course, in this theory we don't really have photons, so the photon here would be, because electromagnetic radiation is not treated as quantized object here, the photon is more like a bookkeeping object. It helps us keep track of what's going on. So we may use a language of photons sometimes, but we don't really need to, and frankly, within the ambit of this theory, perhaps we shouldn't even talk about photons. Now, Monochromatic radiation is not the most general situation. A more general situation would be a situation where different frequencies and different wave vectors are also proposed. So we would get an A vector R, which is essentially given by, it is a I kn dot r minus omega nt. That's the phase part, which is different for each of the modes, times an amplitude which also depends on the mode. And what we are doing here is we are taking the complex part of the phase part of this complex amplitude out for one very special reason. When we say that radiation is totally incoherent, which is the kind of approximation we will use most of the time, the phases here, these phi-ns, will be completely randomly distributed. And what that means, of course, is that if you were to multiply the phases with each other after complex conjugation, you will end up with an average value which is 0 whenever m is n are different. So different modes have perfectly random phases here. Of course, when m is equal to n, you are really talking about the average of 1. So this has to be 1 in that case. So that is why this average is really delta mn. Now this totally incoherent radiation approximation will simplify a lot of our calculations, as you will soon see. Well, what will it do? If you calculate the Poynting vector starting from this A, so you have to calculate the electric field for this A, which will be a sum over all n modes. Then you will have the magnetic field, which will be a sum over all n modes again. And when you calculate the Poynting vector by taking the cross product of E with H, you are going to get lots of cross terms. But all these cross terms, terms which come from different modes, will average out to 0 because of this incoherent radiation assumption. So what this means ultimately is that the Poynting vector will end up being the sum of contributions from individual modes. So all cross terms will vanish. That's what the incoherent radiation approximation does for you. Now, this is for the Poynting vector. If the beam happens to be well collimated, which means all of the modes are in the same direction, or propagating in the same direction, so all of them have a common k hat m, so k hat m is equal for all of them, then the amplitude of the overall thing will simply be sum of these amplitudes here, sum of these magnitudes here. And so for a well collimated beam, I turns out to be sum over all the modes of this quantity 1 by 2 pi omega m square by c a m0 mod square. And because this is a sum over individual modes, I can write this as sum over im, and which also means that if the modes are very closely spaced to each other, what we can do is we can discuss this in terms of a density of modes. We can say I omega d omega is the intensity of light between omega and omega plus d omega. Total intensity will then simply be the integral over all possible frequencies of I omega d omega. So this is the background that we need from classical electromagnetism to continue our theory. Now, with this background from classical mechanics and classical electrodynamics in hand, we will go on and take a look at what this has to say about the quantum theory of light matter interaction, in particular, of course, the semi-classical theory. So what we are going to do is we are going to discuss the theory using perturbation theory to first order in perturbation, and we are going to treat the field, in this case a vector potential, essentially as a perturbation term. So this, of course, is the Hamiltonian, and the classical, this is the classical Hamiltonian. In quantum mechanics, the same Hamiltonian will work, except that here the P will be an operator, so will be the R's. So to first order in the interaction, we can easily expand out the square in this form. So all we are using here is a plus b whole square is a square plus ab plus ba plus d square. And here we are ignoring the second quadratic piece, because after all we are going to do first order calculations in perturbation theory. So anything which is second order in the perturbation anything involving a square can easily be ignored. So this is what we have. Now, in order to simplify this further, let's take a look at what happens when you apply these two terms individually on any wave function. So, pk.a_rk psi can be easily seen to be the same as ark.pk acting on psi. Remember, pk is h cross by I radiant with respect to the kth particle's coordinates, and using simple laws for differentiation, which is straightforward, you have already done that often enough in quantum mechanics, can show that these two things are equal within this additional term. So basically this pk has a gradient, and the gradient actually acts on both the product of a and psi, and when you take the a out, the gradient has an additional term where it's acting on the a, and psi is not touched by the gradient. So it's just basically d dx of uv is u dv dx plus v du dx at work here. Notice that if we are going to use Coulomb gauge, that's the gauge we are using, then this term, which is the divergence of A, simply vanishes. So we have these two terms produce the same effect on every wave function, which means as far as we are concerned, these two operators are the same, which further simplifies the Hamiltonian into this. We have split up the Hamiltonian into two pieces, one involving the A, the other independent of the A. Of course, you can see that the piece which does not depend on the magnetic vector potential is nothing but H0, the Hamiltonian of our unperturbed system. Of course, I may not have stressed this here, but all the M's and all the E's are equal because here only the electrons are involved. The nuclei, as I have said before, are no longer dynamical because we are approximating the mass to be infinitely large. So here you have the Hamiltonian for the original harmonic system, and this is the perturbation. So H0 is given by this, and the perturbation is this. So we need to calculate the effect of this perturbation term. So going back to our lessons from electromagnetism, if we use for the vector A, the monochromatic. So this vector A is sitting here, and of course there is a sum over all the electrons that are there in the system. So if we use a monochromatic plane wave for our incident radiation, what we are going to end up with is this expression. For the V, this is one term, plus of course is Hermitian conjugate. Now you have a Hermitian conjugate simply because there are operators involved. There are no operators in the A0, but the P, etc. are operators. So you have Hermitian conjugates that you have to deal with. Now, if you recall an earlier lecture on time-dependent perturbation theory with sinusoidal perturbation, we actually treated this problem of sinusoidal perturbation where we had f e to the minus I omega t, where f is time independent and some operator, plus its Hermitian conjugate. So this whole thing in red here is the f from that lecture. In what follows, we are going to make use of several of the lessons that we had learned in previous lectures. So this particular video is basically about an application where we put together many of the results that we had learned before. So here, this is f e to the minus I omega t plus Hermitian conjugate, and in that lecture, we had studied this in some detail. So in case you need a recap, please look at that relevant video again. The matrix element that we need to deal with are the matrix elements of f between the initial state I and the final state f. That comes from this term. Of course, we also need the term which comes from the Hermitian conjugate, so that will be f daggers fi element or f star if. That's also quite important. So this is one of the relevant matrix elements, and you also have f star if to worry about. And it's easy to see that the matrix element will be minus E by MC A0 vector mod that goes out. So some is fine. Then you take the matrix element of sandwich between F and I, the final set bra and the initial set ket, this whole thing. So this is your FFI. Now, if we are dealing with visible or near ultraviolet light, a wonderfully good approximation immediately presents itself. Notice that the wavelength of this light is of the order of hundreds of nanometers, so 10 to the minus 7 meters or more, whereas the states that we are sandwiching them between, these are typically atomic states, and the wave functions corresponding to these states die out rapidly beyond atomic dimensions. So the relevant R values for which you are going to get contributions to the integrals involved here are of the order of 10 to the minus 10 meters or so. So within that region, the magnitude of this k dot r, kr, which is 2 pi over lambda times r, is much smaller than 1, because r is of the order of 10 to the minus 10 meters, whereas lambda is of the order of 10 to the minus 7 meters. This means that you can safely take e to the I k dot r and approximate it by 1. So this simplifies the calculation a lot, because all you need to do is worry about the matrix element of epsilon vector dot p, the momentum between the states F and I. This factor can be put equal to 1 safely. And as you will soon see, this is what leads to what is called the electric dipole approximation. Why dipole? You will soon see that. Why is the name dipole used? So now that we have understood that we can simplify this expression considerably, let me just recap. You are setting this equal to 1, and since epsilon vector here is a purely classical object, has no operators in it, we can move the epsilon vector dot outside. So the expression for the matrix element of F between the final states F and the initial state small I simplifies to this expression. So ultimately you have to figure out the matrix element of the momentum operator. Now why do we call this the electric dipole approximation? Well, to understand that, we have to see how we can express the matrix element of the momentum operator in terms of something which is usually easier to calculate. Remember, momentum after all is mass times velocity in a sense, and so at least if you take the commutator of h0 with rk, which remember essentially gives you the derivative of r, you end up with this expression. This is pretty easy to figure out from both the equations of motion or simply by directly evaluating this particular commutator. After all, h0 has pk square by twice m, which is the only part which fails to commute with rk, and after that showing this result is trivial. It's just a matter of evaluating the commutator. So pk, the operator which is sitting here, can be written down as mi by h cross times the commutator of the unperturbed Hamiltonian h0 with rk, the position operator. So the matrix element sitting here is simply this matrix element, the matrix element of a commutator. Now remember, the states I and F, the initial and the final states, are both eigenstates of the Hamiltonian h0. What that means is when h0 acts on these states, you end up with a very simple result. And this is the simplification that we are looking for here. h0 rk minus rk h0. In h0 rk, h0 is acting on the bra f here to give epsilon f. In rk h0, h0 acts on the ket I to give epsilon I, and this is what you end up with. Of course, this quantity epsilon f minus epsilon I by h cross should be pretty familiar. This is nothing but the frequency of quote unquote the photon emitted when there is a transition between states of energy epsilon f to epsilon I. Of course, photon here is just again being used as a bookkeeping device or in anticipation of later results when you actually quantize radiation and get a photon. So this is what the electric dipole approximation turns out to be. The matrix element of FFI ultimately turns out to be the matrix element apart from these factors up here, of the sum over all the electrons, that's what the label K here stands for, of the quantity ERK, where ERK of course is the dipole moment due to one electron, and sum over K is just the net electric dipole moment of the system. So the relevant matrix element, the one which goes into all calculations, essentially is the matrix element of ERK between the states F and I. The electric dipole moment between the states F and I, hence the name. And just by using that fact, we can simplify the notation a bit. You can of course use the fact that this is omega Fi, and often we just take the E out of this expression and write for RFI the matrix element between the states F and I of the total position vector sum over all the RKs. And this is the final simple form that you end up with. Now, what consequences does this form lead to? Well, almost immediately what you can get out of this, with very little effort, are the selection rules. Which transitions are allowed, which states, from which state I can you go to which state F under the action of electromagnetic radiation. Now, you have to just remember one thing. FFI is a relevant matrix element when we are talking of energy being absorbed from the radiation. The energy epsilon F is more than epsilon I. In the case of emission, where the energy of the final state is less than the energy of the initial state, you actually have to worry about the other term in V, the Hermitian conjugate of the term that we have been dealing with so far, and that will have F star IF. Very similar, except for the change in the sign of I. The epsilon vector will become epsilon star, and R Fi, of course, R dagger is the same as R being Hermitian, so it's going to be RIF. So that's all you have to worry about. Right now, let's look at what kind of selection rules you're going to get. And that's really very simple. Now, since one thing we know about this is position vector, which is featuring prominently in the matrix element here, is a polar vector. And that means it changes sign under parity. When you do the parity operation, R goes to minus R. Now, if your system has parity symmetry, which means parity is a good quantum number, that's just a fancy way of saying that your eigenstates can be classified as even or odd. If that happens, then if both I and F have the same parity, that is, they are both either even or odd, then you can see that this matrix element overall will have to be odd under parity, because F and I will either produce both plus signs or minus signs, hence cancelling each other out, and RK will produce a minus sign under parity. So RFI will change sign under the parity operation, but since parity is a symmetry, RFI simply cannot change sign. So in such cases, the matrix element must vanish. This means that the transition can occur only between states of opposite parity, not between states of the same parity. So that's one immediate selection rule. The matrix element vanishes, and hence, at least to first order in perturbation theory, remember whatever we are saying in this lecture is valid only to first order in perturbation theory, but that's a pretty good indicator. The matrix element will vanish unless I and F have opposite parities. Of course, always assuming that parity is a good quantum number, that is, your system has parity symmetry. Now, as far as this matrix element is concerned, this is a matrix element of R, which is a vector operator. So this is where what we studied about the Wigner-Eckart theorem in the lectures on rotations in quantum mechanics comes in handy. Wigner-Eckart theorem tells you in general that the matrix element of a spherical tensor operator component between angular momentum eigenstates are proportional to the corresponding Clebsch-Gordan coefficients. And so the same rules apply as for addition of angular momentum. The Clebsch-Gordan coefficient here, for addition of kq with j prime m prime leading to jm, would vanish unless m is equal to q plus m prime. That's a very straightforward and standard result that we all know. Also, unless j happens to be between mod of j prime minus k and j prime plus k. So these are the selection rules that you immediately get. For the general spherical tensor operator, of course, what is relevant here is that we are calculating the matrix element between states I and F, which are presumably also angular momentum eigenstates of a spherical vector operator. That means you have k equal to 1. So this means that the matrix element that is relevant for this case will vanish, and so no translation will occur unless you have this. Unless the angular momentum Jf minus Ji satisfies plus minus 1 or 0, that's because k is 1 in this case. So Jf can be Ji plus 1, Ji minus 1 or Ji, the three possible values. Remember angular momentum addition, the same laws work here. And one important thing, if Ji is 0, then addition of k can only give you 0, cannot give you plus 1. Can only give you plus 1, cannot give you 0. And so despite the fact that Jf minus Gi is equal to 0 is allowed in general, a translation from 0 to 0, from Gi equal to 0 to Jf equal to 0 is simply not allowed. Now a special case occurs if we can ignore the spin-orbit interaction. If you ignore the spin-orbit interaction, then the atomic states can be labeled, as you all know, in terms of the standard labels L, S, Ml, Ms. After all, in high school chemistry, you actually studied atomic spectra without, or atomic structure, without worrying about the spin-orbit interaction. So L, S, Ml, Ms were the quantum numbers we are studied about. So if your states are labeled by these, then the above selection rules can be simplified a lot more. Notice that the operators whose matrix elements are talking about, either pk in the original version, or after this manipulation that when we are dealing with matrix elements of position vector rk, these operators don't act on spin states. So the only way in which the matrix element will not vanish is both I and F, the initial and final states, have the same spin. So S has to be the same for both of them. And the entire burden of the selection rule falls on L. So now the selection rule becomes SF equal to Si and LF minus Li equal to plus minus 1 or 0. And once again, Li equal to 0 to LF equal to 0 is forbidden for the same reason as before. Now, in addition to that, we can actually take a look at what happens for the MLs or MJs. So because epsilon dot r, this operator here, or can be written down as linear combinations of Rz, R plus, R minus. So the three components of a spherical vector operator. Wigner-Eckardt theorem, once again, and just this, not really the full Wigner-Eckardt theorem, just the fact that Clebsch-Gordon coefficients vanish under certain conditions, immediately tell you that MJF minus MJI, the values of the magnetic quantum number difference between the final and the initial state, must be plus minus 1 or 0. That's because Rz, R plus, R minus corresponds to Q values of 0, plus 1 and minus 1 respectively. And once again, if you can ignore the spin-orbit interaction, the spin quantum numbers must match, so MSF must be equal to MSI, and the selection rule essentially forces MLF minus MLI to be either plus minus 1 or 0. Now, this is a general statement. You can make a more specific statement if you specify which polarization state and direction of propagation you are talking about. So, once you have specified the word vector epsilon and the direction of propagation k hat, you can make more detailed statements about which selection rules can occur. And just to illustrate that, let us consider a special case where k hat is z hat and we consider left circular polarization. So epsilon vector is epsilon plus given by this quantity. Now if you calculate epsilon plus dot r, what you are going to get, because of this x hat plus iy hat here, you are going to get the coordinate x plus iy, which essentially is r plus. So this corresponds to q equal to plus 1. So when now you have to carefully distinguish between whether you are talking of absorption processes or emission processes. We could ignore these earlier because as far as general statements that we were making earlier were concerned, the same rules work for FFI, which is relevant for absorption, or F star IF, which is relevant for emission. But now we have to be more careful. So for absorption, only the terms involving FFI will be resonant, and so the other terms can be ignored. And now the selection rule essentially boils down to the one corresponding to Q equal to plus 1, which means Mj for the final state must be equal to Mj for the initial state plus 1. Similarly, if you use right circular polarization, this changes to plus I by root 2 x minus Iy, that's the epsilon minus vector, and this quantity whose matrix element you are finding out will become x minus Iy. So the selection rule then becomes Mjf equals Mji minus 1. So for specific kind of light, specific polarizations of light, you are going to get this. Either Mjf is Mji plus 1, Mjf is Mji minus 1. These are the two possibilities. For linearly polarized light, which of course can be thought of as superposition of circular, two circular lights, you get Mjf is either Mji plus 1 or Mji minus 1. Now this is for absorption. What about emission? For emission is the other term containing epsilon plus star. Remember, that's the F star Fi. So there's the epsilon plus star which comes in or epsilon star actually, not epsilon plus star. Epsilon star comes in. In general, epsilon plus star if you are talking of left circular polarization. And for left circular polarization, because of the conjugation, epsilon plus star dot r is x minus Iy, essentially r minus, Q equal to minus 1. So for emission under the action of left circular polarization, Mjf must be Mgi minus 1. For right circular polarization, similarly Mjf has to be Mgi plus 1. So the rules for transition switch when you are talking about emission or absorption. Okay. So far what we have done is figured out selection rules, that is whether transitions will occur or not occur. So whether there will be a light emitted or absorbed at all at that particular due to that particular transition or not. Now we can also go further into details. We can talk about rates of emission or absorption. Now these is a pretty detailed calculation, so we are going to just touch the surface. This is already a pretty long video. We are going to talk about how to use time-dependent perturbation theory to calculate the rate at which atomic systems absorbs or emits radiation. And in this context, we are going to use time-dependent perturbation theory's detailed calculations. So notice that in this situation, we have to clearly distinguish between two cases. What kind of radiation are we using? Are we using monochromatic radiation or are we using wideband radiation? Now, no radiation in nature, of course, is perfectly monochromatic, but you must also realize that no excited state is ever perfectly sharp in energy. Because of the finite lifetimes which excited states have, all excited states have a width. So there's a natural line width or energy spread, let's call that gamma, which essentially is a consequence of the energy time uncertainty relation. States which exist for only a limited period of time cannot have a perfectly precise energy. And so you classify states, incident light, as monochromatic or wideband depending on how the spread of frequencies in the radiation compare to this natural line width of the lines that we are talking about. So if h cross times delta omega, where delta omega is a spread in the frequencies, is much less than the natural line width gamma, then you treat the radiation as essentially monochromatic. You can forget about the spread of frequencies, just use 1. On the other hand, if h cross delta omega is much bigger than gamma, you have wideband radiation. So, and typically we will consider incoherent wideband radiation. So these are the two extreme cases that we are going to discuss. Situation becomes a lot more complex when h cross omega, delta omega is of the order of gamma. Close by, then you have to take into account some of the radiation, and also if it's not completely incoherent, polarization effects become important and so on. So those are details which we can all incorporate in the calculation, but that would only make the calculation a lot more difficult and lengthy. If we are talking of specific experimental situations, we will have to do those calculations. But for the time being, we are just looking at general principles. So these two extreme cases will serve us pretty well. In particular, if we are talking of monochromatic radiation, if you have a frequency omega which is pretty close to the energy gap between two states, A and B, where B is a excited or higher energy state, then we know that the atom essentially behaves like a two-level system. You can easily ignore all the other levels because chances of transition between those levels or cause between those levels due to this perturbation, this radiation that has fallen on it, is very, very small. Now, because this is like a two-level system which has been excited by a sinusoidal perturbation, we can make use of an exact solution that we derived in an earlier lecture. This is a good time, if you don't remember, to preview those lectures on time-dependent perturbation theory that we had done the last few lectures, because we are going to make use of the results that we had derived there. So, from the exact solution, we know that the system will oscillate between the states phi b and phi a in such a situation. Of course, there's a typo here, it should be phi b and phi a. And the matrix element that is relevant in this case essentially is the matrix element of FBA, which is the same essentially as the FFI that I had written earlier, except that F and I have now been specified to be B and A, the two states involved. And I can rewrite this using this notion that E times RBA after all is the matrix element of the dipole moment operator, and dBA essentially is the projection of the dipole moment vector. So that's why the name D between the states A and B in the direction of the polarization. So this is your final expression for FBA, or simplified notation for FBA. And we can rewrite FBA mod square, which is the quantity which is going to go into all our equations. Once again, refer to the lecture on the exact solution for two-level systems. We can simplify that FBA mod square expression by using the fact that the intensity of radiation is proportional to A0 square is given by this expression. And using this, FBA mod square can be easily written in terms of the intensity. So this is the exact expression, but since we are only dealing with a situation where omega is very close to omega BA, epsilon B minus epsilon A by H cross, we can safely replace this by this simpler expression. So the matrix element essentially depends on dBA mod square, the dipole moment matrix element, how big that is, and the intensity of light. Of course, we are dealing with situations where selection rules are satisfied, so dBA mod square is not 0. The selection rules automatically tell us in which cases dBA mod square would vanish. So we are not even going to consider those transitions. Even if omega matched omega BA in such cases, transition would not have occurred. Now with a non-zero dBA mod square, the essential thing here is FBA mod, the magnitude depends essentially on the intensity. And why is FBA magnitude important? Because if you recall the results of this exact solution that we had derived earlier, what we know is that the system now oscillates between the states phi b and phi a, and the probability of finding the system at the state B, given that it has started from state A, that's PBA, is given by this expression. So this oscillates essentially at a frequency given by omega, or rather, strictly speaking, twice omega because of sine square here. And omega, this quantity, is essentially given by something which talks about the detuning, how far away omega is from omega BA, and how big FBA is. This quantity is critically important. In particular, if you add resonance, then this factor becomes exactly equal to 1. So it's possible in this case to find the system exactly in the excited state at certain equal intervals of time, and of course exactly at the ground state at the same interval of time but shifted in phase by pi. So that's what this says. The system oscillates now from being in the ground state to being in the excited state to being somewhere in a superposition and back and forth with a given frequency, and at resonance the frequency is exactly proportional to mod of FBA, so it's proportional to square root of the intensity. So how rapidly does the system oscillate between the two states? That depends on the intensity. Now, if you have only two states which are well isolated from each other and well isolated from all other states, then this is a perfectly good result to think about. The system periodically absorbs or emits light from radiation, and the atom goes up and down in energy. Now, on the other hand, if you have a spread of states or rather your frequency range of radiation is spread widely enough so that several states are taken into account at the same time, then we can no longer use this approximation of a two-level system. So we have to fall back upon our results from first order perturbation theory. This is a result we had derived earlier in an earlier video. Once again, I'm urging you to review that. So this is the expression that you have for the probability amplitude or the coefficient for the system to be in the state B, provided that you have started at t equal to 0 from state A, and these are the two terms that come in. One is FBA, that's due to the F term in V. The other is due to the F dagger term, which is F star AB, and they are connected with these sinc functions, one with omega BA minus omega by 2 into T as argument, the other with omega BA plus omega by 2 to T as argument. Now, if we are talking about absorption, that is epsilon B is more than epsilon A, then omega BA is positive, and only this term can have an omega which is close to omega BA, so an argument close to 0. Let me remind you that this function essentially peaks sharply at its argument equal to 0 and falls off rapidly, especially for large times t. It falls off very rapidly on both sides, which means that for absorption this term can produce a large effect when omega is close to omega BA, and for such situations this term is very, very small. So only the first term will contribute, so you will just take that into account, and we have just put in the value of FBA that we had figured out earlier, and this is what you are going to get. So CBT is going to be this expression, and the probability of course is going to be the mod square of this, but more importantly that's for one frequency. Since we are talking about non-monochromatic radiation, you should be able to figure out the result by adding up the contributions from many different frequencies. And there, as before, I have written the A0 as a function of omega, and since A0 in general can be a complex number, I have written this as A0 omega to the I phi omega, where phi omega depicts the phase, essentially the phase mismatch between different modes. Now we need to figure out what is the probability that the system will be in the state B under the action of this non-monochromatic radiation, and we are going to make the incoherent radiation approximation, which is e to the I phi omega minus phi omega prime. This rapidly fluctuating quantity will average out to 0 unless omega is equal to omega prime, in which case of course is 1. And this is where the incoherent radiation approximation becomes very useful. If you take the mod square of CBT to find the probability, you will of course have to take, let's go back to this, you'll have to take this expression and its complex conjugate, multiply them together. Remember to use different summation indices, omega for one sum, omega prime for the other. That's exactly what has been done here. And this phase factor is simply what you get when you carefully use omega for one term, omega prime for the other, multiply one term by its conjugate, you end up with this expression. That's pretty straightforward. But important thing is the phase term here changes rapidly from over various frequencies. So when you're summing up over frequencies, you need to take the average value of those because of these rapid oscillations, And when you do that, this becomes delta omega prime omega, and that simplifies the calculation a lot. You end up with this expression, a very much simpler expression than before. And now we use the fact that at least for large times t, this function essentially behaves like a delta function, or rather 2 pi t times a delta function. We have discussed all this before in an earlier video. So once again, you would find this confusing, go and listen to those videos. So this is your final expression for PBA. It is sum over all frequencies of A0 square omega, which of course brings us back to the intensity, I omega. And instead of the sum over all omega, we rewrite this as an integral, and this is what this form becomes. Pretty straightforward. But now, notice that because of the delta function here, this integral actually becomes very simple. All the omegas in this integrand gets replaced by omega BA. So you have I omega BA, 2 pi c, and these two cancel by h cross by c square into 2 pi, so 4 pi square by h cross by c dBA mod square, and so on. It's a straightforward calculation. But there's an overall t. So the probability that you will find the system in state B increases linearly with time. Of course, that means that this cannot go on forever. This is only correct as long as this expression P for PBA stays small. Otherwise, well, you might say otherwise PBA, the probability might even become bigger than 1 given large enough time. But much more importantly, once PBA becomes substantial, forget being bigger than 1, then the first order perturbation theory approximation that we have done will simply break down. After all, once the term becomes big enough, you cannot ignore second order contributions. But at least within the first order approximations per ambit, what we can easily do is divide this PBA by t, the time, and figure out what is the transition probability per unit time, and that works out to be WBA given by this expression. Now, in many experimental situations, the light as well as the initial atomic state is unpolarized. That is, we do not really know which one of the mj values, possible mj values, there are 2j plus 1 of them of course, it is in. So, also the final state's mj values may not be determined by the experiment. In such cases, we don't really talk about this as a transition probability. This is for transition probability from for a given initial state to a given final state. When your experiment does not distinguish between final states mj values, so all these 2jb plus 1 final states turn out to be considered on the same footing, and you don't know whether your initial state is in one of these precise mj states, what you do is that you can have to average over initial states and sum up over all the final states, all the possible final ending points you can go in. And this leads to this expression. 2jb plus 1, so that's because of the factor 2jb plus 1, that's how many final states, final mj values you can have. 4 pi square by h cross square c as before, because of the fact that the polarization state of light is not precisely monitored or is completely unpolarized, you get dBA square contributions from all directions isotropically. So if you just take the dBA square magnitudes average and divide that by 3, that's for any particular direction. That's the average value you are going to get times I omega BA. So final result, the transition probability per unit time turns out to be I omega BA into a constant which we call BBA. So BBA is essentially what we will soon call Einstein's coefficient for transition from state A to state B. And BBA, of course, is a quantity given by this, which depends on the degeneracy GB of the state B. How many different states are we considering together? That's a 2jb plus 1 times the factor which essentially depends on the matrix element or averaged out matrix element for the dipole moment operator. So this of course was for absorption. For emission, things are going to be very similar. You will get WAB transition probability per unit time from the state B to the state A, the lower state, which is given by a very similar expression. It will be proportional once again to I omega BA times BAB, where BAB is this coefficient. And as you can see, the coefficient is very similar to whatever you had for BBA, except that the degeneracy factor sitting here, GA, is 2JA plus 1, the number of states which your number of distinct microstates which your state A is talking about, as opposed to this one, where you had 2JB plus 1. So in both cases, you see that the coefficients BBA and BAB, the two Einstein coefficients, as we are going to call them soon, they are both proportional to the respective degeneracies, GB and GA. Now, so far all we have talked about is simulated emission or absorption due to external radiation. So both absorption as well as emission were caused by incident electromagnetic wave, and that's easy to see, although that may seem a bit unusual in the sense that why do we need external radiation even for emission? The answer to that is quantum mechanics tells us that a system in a stationary state will stay in that state forever. So unless there's an external perturbation disturbing the system, even an excited state of an atom should actually stay on forever, and there should be no transition. The transition is caused by the perturbation. But this means that an atom in an excited state in a dark room where there is no radiation should not radiate, and that of course is against our experience. Spontaneous emission without any external radiation does occur. This is one part where you cannot explain one part of light matter interaction. Spontaneous emission is one thing you cannot explain using a classical theory for radiation. You need a quantum theory of radiation for this. Although people have figured out a way around this, you often find this explanation that what we call a vacuum for radiation is not really the vacuum. It doesn't have zero electric field. It does have an electric field fluctuation. This essentially is borrowing from Heisenberg's uncertainty principle. And the electric field fluctuates with an average of zero. That's what vacuum really means in this theory. And spontaneous emission essentially occurs because of the interaction with this fluctuating vacuum radiation. So strictly speaking, when people talk about semi-classical theory, they really mean the theory where radiation is treated classically, and in top of that you take into account vacuum fluctuations, which is a result which you borrow from quantum mechanics. You still treat vacuum as classical electromagnetic field, just not a monochromatic fixed field, but something which fluctuates so that its average over time is zero. Actually, it is this theory, that is classical radiation plus vacuum fluctuations, which can explain 99% of the light matter interactions that we talked about at the beginning. But a full-fledged proper explanation for spontaneous emission would require you to treat even radiation quantum mechanically, and there you will see that because of the interaction term between the radiation and the atoms, an excited state atom and the ground state vacuum together do not form a stationary state of the theory. There is a probability for transition from that state to a situation where the atom is in ground state and radiation is in an excited state, that is, has one additional photon. Now, in the absence of a fully quantized theory of radiation, we can explain spontaneous emission by various means, like we can talk of vacuum fluctuations as the cause and actually use the kind of calculations we did on the last few slides to explain the amount of spontaneous emission you have. You can also explain them away by using correspondence principle based arguments. However, what I'm going to talk about now is something which Einstein derived spontaneous emission and various other relationships between this and stimulated emission and absorption from purely physical arguments, and this was done even before the birth of quantum mechanics proper. So these are Einstein's celebrated A and B coefficient based arguments. And how does this go? It essentially goes this way. Einstein considered a situation where you have black body radiation in a cavity and there's a two-level system immersed in that radiation. And let's say this two-level system has an energy gap between the two levels which is resonant with a particular frequency omega present in the black body radiation. So the black body radiation has intensity I omega and energy density U omega, which is given by I omega by C. This U omega is the celebrated energy density for black body radiation, whose explanation by Planck gave birth to quantum theory, old quantum theory at least. We will see that Einstein managed to derive an expression for U of omega using very straightforward, simple physical arguments. And on the way, he managed to figure out the connection between spontaneous and simulated emission and absorption. So in this theory, Einstein assumed that Na and Nb are populations of the ground and excited states respectively. So Na of the atoms are in the ground state, Nb are in the excited state. Of course, Na plus Nb is a constant. So this is not one two-level system. So the A here is wrong. Quite a lot of two-level systems immersed in black body radiation. They are identical two-level systems, but some of them are in the excited state, some of them are in the ground state. Now the population of the excited level will change due to several reasons. One of them will be due to spontaneous emission. So the rate at which population of the excited level will change per unit time is basically the probability of spontaneous emission per unit time, Ws, times the number of atoms which are already in the excited state. So WSNB minus WSNB, that's the rate of population change. Because of simulated emission, again system will transit down, but for that you have the rate which is proportional to I omega. We already have seen this in the last slide, but Einstein just argued this on simple physical principle. Because this is simulated, the rate should be proportional to the amount of intensity of light present times a coefficient BAB. We have already derived BAB in the last part of the lecture, but Einstein just said is some constant times, of course, the number of atoms which are already in the excited state. So this, remember, is the probability per unit time that you will have a transition, and NB is just the number of atoms already. So this together gives you the number of transitions per unit time, and because these are transitions out of the state B into the state A, emission, so the system is going from the excited state to the ground state. That is why this comes with the minus sign. In addition to this, you will also have simulated absorption. So that's a BBA. You're starting from the state A, going into the state B, times I omega. That's the other probability, times the number of particles in the state A. So this, of course, comes with a plus sign. So rate at which NB changes, dNB dt, is going to be a sum of all these three terms. Two decreasing terms, two negative terms because of they decrease NB, and one positive term. Of course, dNB dt must be the negative of dNA dt, because NB plus NA has to be a constant. Now let's focus on what happens under equilibrium. Under equilibrium, NB and NA are both constants, so dNB dt has to be 0. So that's one thing that you must have. And the other thing that you must have is the ratio between Na and Nb must follow the standard Boltzmann statistics. So Na by Nb has to be given by these terms. So the number of atoms in state A will be equal to degeneracy of state A times the probability, relative probability that is in the state A, and divided by a similar factor for B. So Ga by Gb times e to the power the energy difference by kT. So this is Here's the Boltzmann factor. So this is where statistical mechanics comes into the picture. So just by using the fact that at thermal equilibrium this thing is 0, you can solve this for I omega and you end up with I omega given by this quantity WSNB by BBA NA minus BAB NB, which can be of course easily written in this form. Is just divide the whole thing by NB into BBA, and as a result you end up with this expression. So this is what I omega should be in thermal equilibrium. And because NA by NB is already known from the thermal equilibrium expression from Boltzmann distribution, this is what you end up with. Now Einstein looked at several limiting cases. He knew one thing, he knew from basic thermodynamics as well as from Wien's distribution law, that as T goes to infinity, so for very large temperatures, Rayleigh-Jean's law was perfectly okay, and he knew that I omega must go as T to the 4, the celebrated Stefan-Boltzmann law. And so this in fact he knew even without appealing to Rayleigh-Jeans, he could figure it out from basic thermodynamics using Wien's displacement principle. All this is something which you must have studied when you studied old quantum theory. So I omega must diverge when T goes to infinity, but the only place temperature appears in this whole expression is here. As T goes to infinity, this becomes 1. So you must have this result that GA by GB must be BAB by BBA. So these coefficients BAB or BBA must be proportional to the degeneracy of the final state that they are talking about. This of course comes as no surprise to us because we had already derived this a few slides ago. But notice, Einstein did not use any perturbation theory etc. at this time because of course those theories were not even there. Quantum mechanics was not even there at that time when he was doing this. So Einstein used purely physical arguments that at equilibrium you must have I omega given by an expression and this I omega must diverge as T goes to infinity. Okay, so that was one part, and so as a result of course, once you put BAB by BBA equal to GA by GB, you end up with this expression for the whole thing. Now, at low temperatures, Einstein knew Wien's law works perfectly well. So U of omega, which is proportional to I of omega, it's an exponential function. It depends on temperature as e to the minus gamma omega by T. That was already known, very well established by experimental method calculations. So this is only at low temperatures. Now, at low temperatures, of course, this is going to be huge compared to the 1. So you can ignore this. So you do get it to the minus 1 by T term. But this can only match this if EB minus EA is actually proportional to this omega. So gamma k omega for EB minus EA will give you exactly to the minus gamma omega by T. And gamma k you can call a constant, which Einstein identified with Planck's constant. So from Wien's law, Einstein could say that the energy gap would be related to the frequency omega by EB minus EA equal to H cross omega. So on the other hand, at very high temperatures, we must have Rayleigh-Jean's law, which followed from purely classical arguments, and at very high temperatures, both experimentally and theoretically, you would expect Rayleigh-Jean's law to hold. And just using this and using the fact that for very high temperatures, this exponent here is small, so you can replace it to the x by 1 plus x. So it is x minus 1 by simply x. He could easily identify the coefficient Ws on top. And he could show that this has to be obeyed. So BBA GA by GB is of course BAB. So Einstein managed to show that Ws, the spontaneous emission coefficient, the probability per unit time of spontaneous emission, without any external radiation has to be proportional to BAB, has to obey exactly this form. And once you put that into your I omega expression and multiply it by C to get U omega, you end up with this. Okay, you don't multiply it with C here, but you could divide this I omega by C to get U of omega. So this is what you get. And this thing in red here should be very familiar to all of you. This is nothing but the Planck's distribution law. So it is rather amazing that by using plain physics-based arguments, Einstein could actually derive Planck's distribution law, derive the connection between spontaneous emission and simultaneous emission without actually dealing with quantum mechanics. And notice this expression for Ws that he found out is the correct expression, as can be seen once you deal with the fully quantized field of radiation, or at least with vacuum fluctuations. But that is already beyond the scope of whatever first order perturbation theory that we have done in this lecture. So sometimes, especially in the hands of a genius, a purely physical argument can go a very, very long way. Einstein's A and B coefficients are living testimony to that. So we have come more or less to the end of whatever I wanted to say about perturbation theory. There's a lot more, of course, but we will move on to other topics next.